Hello, dear students.
Hello, Professor.
Today we have, as I see, we have the final seminar on this semester, and we are going to listen 5 presenters. One of them about the paper, reproducible paper, and 4 about their results on a master thesis work. We have some changes in plan, so we start from first year student Khue Luu about brain tumor segmentation. Are you here? You ready?
Yes, Professor, I'm ready.
Okay, great. Then listen to Alexey Korolev about his thesis on generalized zero-shot learning for intent classification and slot filling. Alexey, not here. Then Vasiliy Baranov and his thesis results on COVID classification. Vasiliy. Not here yet. Then Watana Pongsapas.
I'm here.
The paper about galaxy detection. You're here, okay. And Rishab Tiwari and his thesis on online tool for linguistic and sociolinguistic studies.
Yes.
Great, let's start. You have 15 minutes for each report. Khue Luu, please.
Thank you, Professor. May I share my screen?
Okay, we can see.
Hello, everyone. My name is Lumen Xiaohui, and today I'm going to present my master thesis. I'm the first year student, and my master thesis is about the brain tumor segmentation with 3D UNet. And my scientific supervisor is Professor Evgeny Pavlovsky. I want to take some time to explain about the data set I'm used in my master thesis. So I'm using the brain tumor segmentation challenge dataset, or the BRAT 2020, which consists of, in the training, it consists of 369 cases. And in each case, we have 4 images and 1 mask. In the image, each of the image is represent one modality of the MRI scan, and the size of it is 240 by 240, and it has 155 slides. And in this data set, there are the more high-grade glioma tumor than the low-grade. And you can see that different images from the data set. And also in this data set, the mask not only consists of one tumor region, but it has 3 subregions of the tumor, and each of the regions consists of different tumor structures. For example, the whole tumor will consist of all structures, while the tumor core only have other structure besides the invasion. It does not contain the invasion. And the enhancing tumor only contain the enhancing part without the necrosis. So you can see the enhancing tumor is the blue area here without the green. So the shape of the enhancing tumor is more difficult, is irregular, and it has some missing, usually has some missing in the part. So it's harder to segment than the other subregions, but we can go deeper into that later. Overall, for this kind of task, the state-of-the-art and other solutions usually have this kind of pipeline or this kind of system. First of all, they will stack all of the image from foreign modality into input, and they put into data transformation. Some of them can crop, usually they crop the image, and then they turn it into a tensor, a different part, and then they augment the data. They can flip it, or they can scale the data, and sometimes some brightness, contrast adjustment can be applied to improve the segmentation of the model. And usually after the data augmentation, the input will be fit into the deep learning model. And after that, some solution apply cross-processing, such as they can remove some segmented part that's very small, and then they provide the final output at the segmentation. And for the final output, it consists of different layers. Each of the layer will represent the sub-regions of the tumor. In my master thesis, I'm going to use the 3D UNet. So many of you may be familiar with the UNet because it's quite common in image segmentation, especially in the medical image segmentation. And the 3D UNet is similar, just replace the 2D with the 3D counterparts, and it still have the contracting, encoding and decoding part, but they only have 4 layers instead of 5 before it go up again. For my master thesis plan for this semester, I'm going to analyze or research the state-of-the-art solution, and also analyze the data set. Then from my analysis, I should come up with a method for the next semester to be experiment, and the last semester will be for thesis writing. And this is some of my results so far. I have read at least 10 of the solution about image segmentation of breast data set. Those are winners, those are top rankings of the challenge from 2018 to 2020. I also read some survey about the brain tumor segmentation, and I have observed some common pattern. For example, I have noticed that the UNet-like model are very common amongst the solution. So I believe it is a pretty good architecture to start with, especially the BRAS 2018 and the BRAS 2020 first rank. They use the same NN UNet, which is the modification from the UNet, and they have some change in the model and the change in the way they rank images. So the UNet-like have actually helped the winner of the 2018 and 2020. Secondly, I have noticed that many of authors have have used all of the 4 modality as an input, And I think only one of them separate the modality differently. So I think maybe I can do something here. I will explain it later, but because the enhancing tumor is pretty hard to recognize, to segment, by combining all of them, maybe cannot help improve the performance of the enhancing tumor. Also, I noticed that the accuracy of the tumor subregions are not balanced. For example, the whole tumor usually have the highest DICE score, while the enhancing tumor have the lowest. You can see from the graph that it have similar pattern for all of the solution from the 2018 to 2020. The blue line, the blue bar is the DICE score of the enhancing tumor. And I have done the first round of my data analysis. For this, I have calculated the pixel of the tumor in the picture. So those are average pixel, number of pixel for each type of tumor in an MRI scan. And I have noticed that the enhancing tumor, the number of pixel belongs to enhancing tumor is pretty small compared to other type of tumor. This is true because the whole tumor consists of the tumor core and the enhancing tumor, which make this make me think that by combining four modality, it's not very good for the enhancing tumor because it has smaller amount. And not only that, on the left graph, you can see that the percentage of pixel from the image is very small, very small. The whole tumor usually, as on the average, only consists of 1% of the image, and the enhancing tumor is even lower than that, only 0.24%. So it's very small. So I think we can consider this problem as imbalanced data problem. So we need to have some kind of solution for this problem. And also I've done some visualization of the data, and I have seen that the enhancing tumor shape is pretty difficult compared to the whole tumor and tumor core, because they are usually a full image, and enhancing tumor shape is not only irregular but also have a lot of missing part from the inside. So based on my first round analysis and from my summary from reading the state-of-the-art solution, I have refined my problem into from a broader, more general problem statement into a more specific one. So in this master thesis, I will try to improve the performance of the deep learning model on enhancing tumor in the brain tumor segmentation task. And I believe by improving the segmentation DICE score on the enhancing tumor, it's also help improve the model in general. And it also has some meaning in a medical perspective, because at the end of the day, this kind of solution is helping the doctor to in the treatment. So my approach for solving this is, first of all, I will need a thorough and more detailed error analysis. So this time I'm going to need to run a model, pre-trained, maybe just a pre-trained model on the data set, and then I will get the prediction and analyze the output from the prediction based on the sensitivity and specificity Also, I want to look at the segment of the enhancing tumor to see if it's usually over segment or in the segment, etc. More things like that. So I will spend more time on the error analysis. And then I will do 3 experiments. So the first experiments will be data-centric approach. In this approach, I will try to improve the data instead of fixing the model. And by acquiring more data, I will combine public data sets, maybe train the model with different data sets so that it has more learning example from the enhancing tumor. Also, I will try to apply data augmentation techniques that have been stated useful for the data segmentation in brain tumor. I have read one paper that they state that the elastic transformation combined with the gamma correction can actually improve the performance, and they have tested it on the PRAT 2020 dataset. So I would like to try this. And if it's not improved, then I will try to train the dataset with a similar shape, because the shape of the enhancing tumor is not very regular. So maybe have more things with irregular shape to train the model, and then can train the model again on the PRAS dataset. The second approach will be model-centric. So this time I will focus more about modifying the model than fixing the data. I will change the some contracting parts of the 3D unit. I'm thinking of training a model on different modality and different models. Also in the PRAT data set, they also state that the enhancing tumor appears more on the T1 modality with contract enhanced. So I would like to focus on that modality. I want to have a different model for that, and also try a modify loss function, because the number of enhancing tumor is smaller than the background. So I would like to have more penalty for it when it segment incorrectly, and then I can combine the result from different model. Then I would like to also apply some techniques to handle imbalanced data. I have read some paper about it, and there are some useful technique I would like to try in this step. And the final approach will be combine the best solution from the first approach and the best solution from the second to see if it's actually improve even more. And then, yes, and my timeline for doing this from this semester to next semester will be for next month. Starting from next month, I'm going to I will focus on doing the error analysis and research more about the handling imbalanced data for the whole month. And from this actually from July, I will start with the data-centric approach. From August until September, I would spend 2 months on the model-centric approach. And from October to November, I will combine all of the approach, and the December will be saved for writing the report. That's the overall timeline until next semester. And that's it. Do you have any questions?
Thank you. Please, questions? I just have a note that you will prepare like kind of research plan until the end of this year, and it's good. And you also proposed several hypotheses. Of course, these hypotheses will be refined during implementation part. But at the moment, it seems that it's a good prepared research plan for your midterm work. So, any other questions, comments, maybe advice? No comments. Okay. Thank you for presentation.
Thank you, Professor. Thank you, everyone, for your time.
And let's continue our seminar. Alexey Korolev, right here.
Yeah, I'm here.
Yes, please prepare your presentation.
Excuse me, Alexey, could I switch with you? I have an urgent to leave soon.
Okay.
Thanks. Good evening. Today I'm going to present about a paper, Galaxy Detection and Identification using Deep Learning and Data Augmentation. It was done by the three authors. I'm sorry, I could not pronounce their name. Let's start. They present a method of galaxy classification and identification with a Python package, AstroCV. It was a computer vision library for processing and analyze astronomical data sets. They took data sources from Galaxy Zoo, which was a public online data set, which in which the data has been annotated by 100,000 of people, and also the data are from Sloan Digital Sky Survey, and they implement the model with YOLO method. The data set, the objects of interest were classified into 5 categories. I mean the shape of those galaxies. They classify into elliptical, spiral, edge-on, do not know, and merger. And those data were obtained from 52,000 field images, and they were split into subsample 1 and 2. Then they select only the galaxy which has a size bigger than 22 pixels box size, and about 7,400 field images will remain for its subsample 1, and another about 12,000 images for subsample 2. Here are more detail about the data set. The S1, the subsample 1 and 2 are split into training and validation, and these are the number. And also they add custom data set which they took from Hubble telescope data. And during the training, they apply data augmentation such as rotation and like rotations and brightness adjustment with this field, in which they call a filter. These are the brightness adjustment normalization. And they set up the training data set into six group. Each group has a unique number of images and the applied filters. They apply YOLO for training the model, and here are the training results. The left figure shows the result of the first 3 training model, T1, T2, and T3. And they claim that the training set T2 return better results than the others because of higher contrast and good brightness, so that it emphasized the disk galaxy to be detected better. And for the remaining 3 training set, T4, 5, and 6, they claim that recall and intersection over union score will remain similar. However, the model is more robust, which is, it's less fuzzy, it's more linear, more stable. And the average accuracy of their implemented model was about 0.8. The table 3, they took only training set number 2 as a benchmark. And for table 4, they select training data set 4, and the average accuracy were quite similar. And here are the score of recall ratio and intersection over union ratio for each training set. And for IOU, the scores were acceptable, but not that decent. And recall ratio were quite low. And this is an example of the detected galaxies of the input images. 44 objects were detected. And this is another result. Actually, it was the same images, but when they apply T4 filter, T4 is all of those filters, they obtain more number of detected galaxies. And here are some part of the code. These sets of codes are for data preparation, and it's mostly done by Astro CV library, and use pandas to modify the input in tabular form. And this set of codes for data, the model to detect the object. And that's all.
Questions, please.
What is the scientific novelty of your thesis?
It's not thesis, it's a report on a scientific paper.
Oh, sorry.
Vatana, what was the hardest part to reproduce results?
Could you repeat the question?
What was the hardest part of result reproduction?
Hardest part is to, I think, it to understand it, the data set. I mean, the input is quite different from what I have learned, just as MNIST or another common data set. This one is new to me.
Okay, I see. So, other questions?
Do you need to annotate the data by yourself, or it's already ready?
It's already had been done on
Okay.
Galaxy Zoo.
Okay.
Okay. So then, thanks, Watana, for presentation. And we continue with Alexey.
Can you see my screen?
Yes, we can see.
Okay. Hello everyone. I want to present my master thesis, Generalized Zero Shot Learning for Intent Classification and Slot Filling. My scientific advisor Bondarenko Ivan and Batura Tatiana. Here is content of my presentation. Let's start. What is DST? DST is part of dialogue system. And during dialogue, system try to recognize user intent and fill appropriate slot. What is intent? Intent is intent is what we want system do. So, for example, if you want from system to search fly or reserve table, this intent. So for different services, we have different set of intents and set of slots. If we want to extend our system, for example, include new services, we need to provide new train dialogue with these new services and retrain our system again. And it is quite hard and take a lot of time, take a lot of computational resources. So good method to handle this situation is zero-shot learning. So zero-shot learning is a class of task when during training we have generalized zero-shot learning is task when we during training we have classes. We have seen and unseen classes. Unseen classes is classes which didn't on which we didn't train, but on which we test our system. So we have, so during training, some classes for us is unseen. And for all classes, we have some kind of description. It can be a set of attributes, it can be a text description or something else. And they still trying to understand, to extract information, knowledge between a class description and a class example. And of course, many researchers try to zero-shot approach in dialogue tracking. As we say, as aforementioned, we say that it's can be very useful for dialogue tracking using zero-shot. And nowadays, a lot of architecture are based on BERT or another BLSTM network. And in this system, we just concatenate user utterance, concatenate dialogue intent description, intent attributes, and put this big vector in BERT or another BLSTM. So why it's bad? Because, as we know, BERT have a square complexity. So if we have a big input vector, it takes a lot of time to train this model, to infer from this model. So that's why we use another methods. So first of all, we create zero-shot val. Zero-shot val is it's a special framework for zero-shot task, for zero-shot experiments. It consists of different modules, and you can implement your zero-shot network, or you can use already implemented networks with your dataset and acquire some result, some quality of some result of your experiment. So we with team create this framework for our experiments, and now in this framework we implement two zero-shot nets, KDY and ListBen. Both of these network are used for only for computer vision task. So idea of our work is trying to use this network from computer vision area in our NLP task, in the dialogue static task. Let's talk about this network. KDY is network based on variation autoencoder, and ListGAN is based on generative adversarial network. So it's both of these networks are based on different architectures. So it will be very so we can try both this network and see if it's work on our NLP task. So for datasets, for dialogue stacking is very popular task, and we have a lot of datasets. But we choose DSTC8 dataset because it's special dataset for zero-shot approach in DST. And this dataset have already different services with different intents, and all services and all intents have descriptions, have different attributes. So we can easily use these datasets for our experiment. That's why we use these datasets. First of all, we tried to split our data in different ways. First of all, we unite all intents with same name, but different. Oh, sorry, here's mistake. But different services. So, for example, if we have two services, two airline services with intents, for example, buy ticket, we unite this intent as one and unite all samples. In the second scenario, we consider similar intent in different services as different, and in the third scenario, we it's the same, but we use not only intent description but also services description. As encoders, we use during work we use different encoders. We provide experiments on three types of encoders, three architecture of encoders. First of all is Roberta, XML Roberta, and universal sentence encoder. So all these encoders are sentence encoder. So we just get sentence in this encoder and require some vector, and use this vector in our network. Okay, here is the result of our experiment. So we so here result of experiments with different scenarios. As we can see, they have very interesting feature. For example, first scenario gives very good seen accuracy, but not good unseen accuracy. It's because we unite intent with because we unite many similar intent with same name. So third scenario is gives better result, and we can explain this because in first scenario we have services description, but in second scenario we have only intent description. So that's why third scenario gives better result than second scenario. Okay, here is the result of different encoders, and this is also quite interesting. So we can see if we use XML Roberta encoders, it gives much more better accuracy than Roberta or universal sentence encoder. So that means that encoders effect on the result. Encoders influence on the result, and maybe in the future it makes sense to use another more complex encoders, for example. And here is table with result of this GAN. As we can see, this gun almost give very pure result, and it means that a model based on generative adversarial network can't generate samples for extreme classes, and maybe use this maybe using this and maybe use this type of network inefficient, are not good, didn't get good result. So it's better use network based on variation of the codecs. So conclusion, during this work we test opportunity use the architecture from computer vision task on NLP. Also we try different splitting and different encoders, and provide experiment result and their interpretation. Also some also we developed the zero-shot framework, which can be useful for not only for this work, but in another zero-shot learning task, zero-shot learning research. And thesis of this work was accepted in the International Student Scientific Conference. That's all. Thank you for your attention.
Thank you. Please, questions? Do you have comparison with state of the art for with state of the art for results on this data set?
Yes,
Do you have comparison with state of the art?
Yes, unfortunately, our decision gives worse results than state of the art. But one of the problem is that in state of the art, maybe in state of the art, researchers have different splitting, and no, it is correct to compare our result with state of the art, but yeah, our result are worse than state of the art.
Okay, I understand. Other questions? Okay, thank you again. And let's continue with presentation from Vasiliy Baranov. Vasiliy?
Yeah, 1 second. Yeah, so can you see my screen?
Yes.
Okay, so today I would like to present my thesis. The topic is classification of COVID-19 in computed tomography using deep neural networks. My scientific advisor is Professor Vladimir Berikov. So, this presentation, first I'll tell a bit about some previous works on this topic, then about used data sets, a few proposed methods, the results obtained by these methods on some benchmarks, and conclusions and further work. So introduction. So in the past 10 years, deep learning in medicine was actively developing because of the large amount of different annotated images and new introduced data sets. The computing power increased very rapidly during last 10 years, and a lot of new algorithms were developed, like different architecture of CNNs and so on. So there are two main methods for detecting presence of COVID-19, which are PCR and CT of chest scans. So actually, the advantage of using CT scans is the speed of diagnosis and higher sensitivity compared to the PCR. So in the work COVID CT dataset, a CT scan dataset about COVID-19, the authors built an open source dataset COVID CT. For this, they parsed large amount of scientific papers and collected the images which were given as examples in these papers. So they collected both COVID-19 and they collected images with and without presence of COVID-19 on these CT scans. And in their next work, they proposed an algorithm which used contrastive self-supervised learning to classify COVID-19 and got some metric results on the COVID CT dataset they proposed earlier. So first about so basically most of the works on medical image, they focus on one type of data. It can be classification data with only labels, with only label for whole image. It can be segmentation data where for every pixel we have some label, and or detection, where object detection, where we have bounding boxes for the objects. So but in the most works, the authors only use one type of the data for their methods and experiments. I wanted to try to use a few types of different data to incorporate the best of the different data sets and different types of data. So for classification data set, I used the COVID CT data set proposed by the authors on the previous slide. It consists of about 350 COVID and 400 non-COVID CT images from 216 patients. And the authors also provided train, validation, test, split. Below are a few examples of such images. As I said, they were collected from different scientific papers. Then I also used a semantic segmentation dataset. It's called COVID-19 CT segmentation dataset. It consists of 100 CT images from more than 40 patients. The training images, the total dataset consists of 100 slices of 512 by 512 pixels size, and the masks consist of 4 channels, which are ground glass consolidations, lungs, so the other part of the lungs, and background. So for training my network, I used only ground glass and consolidations, because these two classes show that there might be something wrong. So these two classes don't point directly to the presence of COVID, but there is some underlying connection, some correlation between these ground glass consolidations and the presence of COVID. And so I hope that my algorithm would find these indirect connections. So, and so I the first method for joint for training on is, I called it joint method. Basically, it is a UNet with where after the encoder we add a separate classification branch. So this approach isn't totally novel. There are different works where where people use UNet or other semantic segmentation network, where after the encoder they build a special branch for classification. But in my case, what I had to do is, since for segmentation images, we know that they are from the COVID patients, but the classification images, they can have COVID, they cannot have COVID, but we don't know the exact masks for ground glass and consolidation, and it's quite impossible to label. So so what I used for this is is the cross entropy loss was counted for all the images in the batch, and the above binary cross interpolation plus dice loss was calculated only for the images which had the masks. So basically the upper part, the UNet decoder, the classification branch, it got weights updated every time, and the upper branch, there were in some cases the backpropagation didn't go through the UNet decoder. So this is the first method. The second method I called two-stage method. First, I trained a regular UNet for semantic segmentation on only the segmentation dataset. Then I used this model to run on all classification images and predict two masks, ground glass and consolidations. Then I stacked these two masks together with original 3 channels for the image. So the images now were 5-channel, and I trained the classification model ResNet 26D to classify these 5-dimensional 5-channel images. So the intuition was that the segmentation masks might point to the region of interest, and they might help the classification network. So for the results, I built a strong classification baseline. Then we see it in the first line. Then there's joint model two-stage method, and a single network, regular classification network, the best from paper 2. They also proposed it as a baseline, and dense net with self-supervised learning pre-training. For this task, they used additional lungs dataset with lungs data, which consist of about 800 CT scans of chest CT scans. So the classification, my classification baseline, actually, all the models were evaluated on the same test set proposed in the article 1. So the classification baseline was a bit stronger than the classification baseline from paper 2. So joint model was better by about 1%, and two-stage method was the best, like 2% better than classification baseline and 1% better than joint model. And it was a bit worse than the self-supervised learning method, but it also used additional data. So so the datasets weren't identical. And also other conclusion is that actually so in my opinion, the best method is two-stage method, and also it was a bit faster because joint model had to train for quite a long time. So it was training for more than about 80 epochs on the data set, which consisted of both classification and segmentation images. And the two-stage method, the segmentation network, trained for about 4 epochs, and the classification model got the best score for about 10 epochs. So actually the segmentation masks, which we added, they helped to learn the useful information much faster. So in total, the two-stage method, if we count time spent on training, it was actually faster than the joint model. So I prefer it the most out of these three. So, and about the conclusions. So in this work, we developed 2 methods for COVID classification using classification and segmentation data, and also built a strong baseline which we compared with. And as further work, it might be necessary to test these methods on larger data set, because the used data sets were actually quite small, so it was enough to develop these methods and get some metrics. But for further use, like clinical, it's necessary to test on larger data sets. Also, it would be interesting to check how, so in this work we used segmentation data to improve classification task, and it would be interesting to try to develop some methods to improve the segmentation task using classification data, which is harder because it doesn't have any masks. And also one further direction is to actually work more, try to look at self-supervised learning, because it seems to be developing quite rapidly last, I would say, 5 or maybe 4 years. And when we have large amount of data without labels, it is a very good method to use. So these are the main conclusions. That's it. Do you have any questions?
Okay, seems no questions. Thank you for presentation.
Okay, thank you.
And we have the next final presentation for today from Rishab Tiwari on his thesis on online tool for linguistic and social linguistic studies.
Hello all, are you able to see my screen?
Yes.
Okay, so the topic of my master thesis is online tool for linguistics and sociolinguistic studies based on Winchester material, and it is mainly based on names and occupation material that is based on Winchester. So I will introduce like about my thesis. Though my approach is to provide an analysis of Winchester data using image recognition for converting these Winchester data into text, and then apply natural language processing techniques to provide a search tool for linguistics and sociolinguistic studies. And I use and to provide an information retrieval model based on Winchester data. So the data that we used in this thesis is the survey of medieval Winchester, and it in this Winchester material, each individual entries is mentioned in the form of family name, given name, dates, and the occupation related with these names. So first of all, the first process that we done in this master thesis is to extract data from the PDFs, because these PDFs is not in the normal form. It is mainly sketched, or there are some marks on this PDF, so it is difficult to extract this data from the normal techniques like PyPDF2 or any other libraries present. So for this, I used optical character recognition, and for this I use PyTest Direct library in Python. And by using this library, I was able to convert almost all text data that is in the form of PDF or JPEG images. And you can see the result, the text data that we get from the images like this. So we used this library, and the next process is the data processing techniques for NLP. So first of all, we use tokenization to tokens, token our text data. Second, we remove the stop words from our data so that it will not, because stop words didn't give any meaning when we are using our data for the NLP task. And the third process is that name entity recognition, and name entity recognition is used to detect entities from the text like person, occupation, or country name. But in this task, we have to detect entities like name, surname, and occupation and year. So we have to retrain our species name entity recognition model based on our entities. So for that, first of all, I labeled the text data according to own custom entities, and then I retrained the model. And after that, when we applied to our text, it is able to detect name, surname, occupation, and the year related to this data. So we say we can use this model to detect names, surnames, and occupation in any of the data which we want to use. And third step is to create an information retrieval system. So I will explain you the architecture of this information retrieval that we used. We used a corpus of data that is from Winchester, a transformer library to build an information retrieval model, a hashtag library to scale the information retrieval model to thousands of documents, the documents which we have, and to build a search engine. And I use two-BERT model trained on a squared data set, that is Robert base squared and DistilBERT encased distil squared. So I will explain you my architecture for this information retrieval system. First of all, we convert our text data in the form of dictionary in document search, and then document search uses this dictionary, and it uses Elasticsearch to for each of our query, so that it can search in the whole documents about our query the exact answers. And the retriever is used to eliminating documents that we have a little chance of being relevant to our queries. So retriever remove all of the unnecessary information related to that query, and it uses a dense spaces retrieval, and it uses like a collection of tools for cutting, for the question answering model or for information retrieval model. And then the information goes to reader, and reader is basically a transformer based question answering model that is trained on squared. So for this we use two models, like I told you, one is Roberta and other is DistilBERT. So Robert is also a extension of BERT, but it is used by training the module longer time and with big batches of data and for more time. And DistilBERT is like a small, cheap, and light transformation. It has like 40% less parameters, and it is faster in processing, and it preserves over like 95% of BERT's performance. So like applying this architecture, this is the result that we get. Like if we are querying any information regarding name or surname, then it searches the text and giving me the related information. So this is my result right now. And so in this paper, we provided a framework of information retrieval system based on custom data and different natural language techniques to extract data from image and pre-process it from machine learning models. It shows that DistilBERT provide more accurately answers as compared to robot in information retrieval. In this work, we provide a custom-based entity recognition model for custom entity recognition for computational sociolinguistics doing research in this field. And we can use this approach to get information from old archives which are still not in digital form and accessible by the researchers. So scientific novelty related to this thesis is like this work gives approach of NLP and machine learning techniques to work in computational linguistics, customized in an AR model for name, surname, and occupation material. And researchers and students working in this field can use this type of information retrieval to extract information. And we can use this approach to get information from all archives. Future work is to get more structured and specific result based on our query that is mostly linguistics or sociolinguistic based, and to add more data available from other sources to make our more data set and get good results, and to make API for this information system for easy user interface so that anyone can use it easily. And publication, my abstract is submitted and approved in 5th International Scientific and Practical Conference. Thank you. Any questions?
So it seems how this tool can be used, what the interface it has.
Right now it's not an interface, but we have only the type of system in which you can type any query based on name or occupation or year, then it will give the relevant service, relevant searches from the data we have from the Winchester. So right now we don't have such fully interface for that.
Okay, understand. Other questions? No questions, then thanks.
Actually, Professor, I need to show my reproducible report for the paper that I have presented before. So can I present? It
Yes.
will not take.
Yes, we can present.
Thank you.
So now we can we have some time to present cocktails, how to say, all undone work. There is a chance to present now.
Okay, so I will not take much time. So the topic of my paper was resonance, and it's also called the split attention network. So I will introduce about this. In this paper, the author just suggested a new resonance-like architecture that incorporates attention across the feature map. And if we compare it to previous attention models such as SCNet or SKNet, the new attention block applies the squeeze and attention operations separately to each of the selected groups, which is done in computationally efficient way and implemented in simpler modular structure. So the motivation behind this paper is to ResNet models are originally designed for image classification, and it is not good best suitable for other tasks because of the limited size of the receiving field and the lack of cross-channel interaction. And it is to improve the performance of specific computer vision tasks that require network surgery to modify ResNet to make it more effective for specific tasks. And also it's a very ResNet is also consume very much memory. So for that, researcher proposed this ResNet structure. So I will explain a little bit about residual and attention network. A residual network consists of residual units or blocks which have skip connections, also called identity connection. So it is used to create deep netted network in which we are having a degradation problem due to adding more layers. So we can use this. We use residual networks so that it can remove the degradation problem in our models. And the attention network is like I can explain like focusing on specific parts of the input has been applied. Like in this, we have a key and query pair for each specific part of input, in which every value has associated key, and the key is the value itself for the self-attention model. And the architecture of the resonance model, I will explain you briefly. Like in this implementation, all features are divided into K groups, where K is the cardinality hyperparameter, and the radix hyperparameter R indicates the number of splits within the cardinal group. And within each group, the network calculate the attention weight across all the splits and apply and multiplies by each feature map and adds them together to generate the output representation. So these are some results from the paper, like image classification result on ImageNet and other. So I will show you my result. Like I applied ImageNet classification and using ImageNet and using my own image data set and comparing our resonance model and ResNet model. But in my case, like I get like better result I get from by applying ResNet. So I applied average mean error of 34% in ResNest, and I got the 29.17 average mean error in the ResNet. So my results are not according to the paper, but it's slightly different. Thank you. Any questions?
Students, be more active, ask questions. Okay, seems no questions. Thank you, Rishab.
Thank you. Thank you all for your time.
Great. So thanks. We have maybe we missed someone who still not delivered the topic or presentation on paper. Okay, so I need to finalize our academic seminar results. That I summed up on the activity from February, March, and April. May still under calculations, and like what I can say, if we the reference time was 876 minutes. That's a total like full time of attendance, and we have and what we have. Do we have someone who can? Okay, cannot say directly.
Professor, in the meantime, can I ask a question?
Yes, please.
For the enterprise practice, is there a specific format we need to share with our employer to send you, or what they need to specify in the email?
Tasks given to you, hours. So please put real astronomic hours, not academic hours. In we by ourselves multiply by the coefficient that you know. Academic hours are 45 minutes and astronomic hours are 60 minutes.
Yes.
So we by our own recalculate. So your like requirements for enterprise practice is to achieve 540.
Can you hear me?
Yeah.
So in astronomic hours, there will be, like, you may calculate how much. So it's 405 hours in astronomic hours. The exact these hours we need to see from your employer.
Okay.
So any evidence provided by them. If the communication by you, then we need signed letter from manager. If manager can send us the letter, then we not required scanned copy. So we need some like verification that exactly the manager confirm that you spend enough time practicing on the topic of big data and artificial intelligence.
Okay.
So kind of other, so in this activity can be accounted as data set labeling, preparing machine learning models, pipeline, training pipeline preparation, some consultancy on data mining, also some analytic works, elaborating requirements on data science projects are also to be accounted. What we do not account, like web development, not to be accounted, Java development. Partially we can account Scala development because it's related to big data processing. Scala is distributed language for distributed computations. So if you have done with like parallel computation, GPU, it's also to be accounted. So all this to be verified by our laboratory, which is responsible to ensure your enterprise practice.
Okay.
Actually, we officially have not done with directing you to officially to your practice place. So that's why our laboratory is from the point of our university. Our laboratory is responsible for enterprise practice. So that's why we need some evidence you really done some work. We also count your hackathon participation if the hackathon is related to data science, like Samrup Kazanavos hackathon one. And actually the activity on your this hackathon was to invite students, but the project is related to data science, and we, in exceptional case, we account this activity.
Apart from that, we also took the, participation in this hackathon as well.
Yes, so we account this activity as organizers and as participators. So you may count the number of hours. And,
Should the manager send the letter to buyer's address?
yes.
And one more, if the exact tasks are under NDA, is it okay just to list like is more general, like machine learning, data labeling, Python software development, like this general, and by hours for these classes?
Actually, we can sign non-disclosure agreements, but please refer to Bayer Nikolaevich, like send the letter from manager. So in that case, if it's disclosed, like you have agreements, your personal agreements on commercial and needs not disclosure, in that case, your manager need to control the information distribution. So we wait from a letter from the manager to Bayer Nikolaevich confirming your hours by direction. But the better case if you provide details and we can sign MO like NDA.
Okay.
So as I see, by 3 months, February, March, and April, more than 50% are like attended by all students. But as I know, some changes were in schedule and like calculations need to be more tricky. So I suppose by finalizing today's meeting, I get additional information, then check again.
And one more thing, from which month we should count our 4 semesters enterprise practice hours?
So hours spent on practice cannot be accounted twice. If you account it in previous semester, then we cannot account the same, like spent time on previous semester. That is general rule.
For 4th semester, because I have some internship in 3rd semester, which I was not able to fill or update you, and so I have to fill those as well.
Okay, yeah, it's viable. So you can fill.
4th semesters internship start from which month? From which month you will count that this hours comes in 4th semester?
You may account activity not being accounted from previous semester, yes.
Okay.
But not like November, December, good.
From internship which start from November comes under 4th semester.
We actually, the 4th semester is started in February.
Okay.
So as exceptional case, we can account. Please write details in your report.
Thank you.
Professor, may I ask what is the deadline for this letter?
It's for 2nd year students.
Okay, sorry.
The first year students, we account your enterprise practice work, you working on the projects, on tool selected projects, we're looking on system analysis and project management. So we account this. And if you have another activity, also can be accounted, but I didn't claim the information gathering now. So now like later. Okay, so since all questions are asked, and Rohan asking about what about those who did freelance work? Clients don't feel any obligation to provide the work statement. So, but like you can, Rohan, you can provide us kind of your tasks on freelance task. You usually, I don't know how it's, you participate in projects or perform some distributed tasks. I don't know. Like short description, the task, hours in freelance. I know that hours are calculated and credited. Okay, so congratulations you with ending of the academic seminar course, and please wait maybe 1 hour to receive your marks on this course. All students will be notified in chat. And see you later, second year students on course on defense, and first year students on coursework defense. Goodbye.
Thank you.
Goodbye.
Goodbye.